Alrighty, so the problem, or in this case, theorem that I chose to focus on for this project was the Pythagorean theorem. So the basics of the Pythagorean theorem. So I got this definition from the Britannica Encyclopedia website that states that the sum of the squares on the legs of a right triangle is equal to the square on the hypotenuse. So with this, we get the equation a squared plus b squared equals c squared, where c is the hypotenuse and is also the opposite of the right angle. So this is going to be the hypotenuse over here, and it's also going to be the longest side. And then a and b are going to be the other two sides of the right triangle. So here we have an example of a problem that we might use the Pythagorean theorem on. So you can notice that we are missing one side, and that's marked by x. And then we also have another side length of 15, and then a hypotenuse length of 21. So we're going to see how the Pythagorean theorem works. So here we have the equation, and we see here that we're missing a, b is going to be equal to 15, and c is going to be equal to 21. And so we plug that into our equation, so we get a squared plus 15 squared equals 21 squared. We square the numbers, do some simplifying, and we get a squared equals 216. And then you take the square root of both sides, get the square root of 216. And from simplifying, we come to the number 6 root 6. And so what that means is that that side A is going to be 6 root 6, side B is going to be 15, and side C will be 21. So what this means, if we're putting it in terms of the Pythagorean theorem, it means that 6 root 6 squared plus 15 squared will be the same number as 21 squared. And that's what the Pythagorean theorem is trying to show. So the history of the Pythagorean theorem. It was named after a Greek mathematician named Pythagoras, who was born in 569 BC and died in 475 BC. Pythagoras was one of the first who came up with a proof for this theorem. This theorem actually has a lot of proofs. If you research it, you'll see many different renditions of ways of proving the Pythagorean theorem. But there really was no date of when it actually got discovered. But another quote from Britannica Encyclopedia says, 4 Babylonian tablets from circa 1900 to 600 BCE indicate some knowledge of the theorem, or at least of special integers known as Pythagorean triples that satisfy it. So we'll get a little bit deeper into this later, but it was an idea that was around a lot, actually. Pythagoras was introduced to the ideas by Western philosophers Thales and Anaximander. And a quote from ancient website, Pythagoras thought that numbers were not only the way to truth, but truth itself. Through mathematics, one could attain harmony and live an easier life. So I just think this is a really cool quote from Pythagoras because it really shows his mindset and shows where he was with things and shows why he might have been successful in this time with this specific theorem. And here's just a couple different examples of some images that you might see proving that the Pythagorean theorem is true and it does work. There are solutions. And we'll specifically look at this one. So what they did here was they made a right triangle with sides A, B, and C. And from those right triangles, they made squares. And for A, each side of the square is obviously A, so they made a square that's a 3 by 3 square. And for side B, it is going to be 4 squares, so they made a 4 by 4 square. And then for side C, they made a square that was 5 by 5. So quite simply, if you count the number of boxes in each square, for the first one, you'll find that there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for side B, there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 boxes. And if the Pythagorean theorem is true, there should be 25 boxes in the square above the hypotenuse, which there definitely are, because you can see 1, 2, 3, 4, 5 squares by 1, 2, 3, 4, 5 squares will be 25. So this is just concrete proof of the Pythagorean theorem being true. This is just one of the simple proofs. I think it's the most easiest one to understand, but it definitely proves it there. Some other mathematicians that were working on the theorem at the time obviously was Pythagoras, and then there were some Babylonian mathematicians that were taking looks at this too, and then there was also Chinese mathematicians that were going to be taking looks at this too. And we found the information to this on Mathematica's website, and then some applications outside of the math world would definitely be in architecture and construction. For example, trying to find the different lengths of roofs or walls, or how high something might need to be, or how high something will be. And another application for this would be in navigation. And we can see this from the sciencing.com website. They say, for instance, if you are at sea and navigating to a point that is 300 miles north and 400 miles west, you can use the theorem to find the distance from your ship to that point and calculate how many degrees to the west of north you would need to follow to reach that point. So that's just some examples of how we could use the Pythagorean theorem outside of just math. And the relevance to the Pythagorean theorem is that it's the basis of trigonometry, really, and it also connects the bridge from algebra to geometry, and it is taught in every single student in every single school when they're learning about algebra and geometry. Um, so it was a great invention. You can do many things with it, and it's truly a very interesting theorem to be studying. There's a lot of history behind it. Some interesting information that we have, like I spoke about earlier, there actually were some talks of Babylonian mathematicians coming to somewhat of a similar proof to the Pythagorean theorem, but instead they found some special cases. Those special cases are Pythagorean triples, which do work in the Pythagorean theorem. They'll always work in the Pythagorean theorem, but Babylonian mathematicians were talking about this way before Pythagoras actually proved the general theorem for it, which is pretty interesting, I think, because the name is of the theorem is named after Pythagoras. I think it's interesting that there were some people beforehand who made some pretty major contributions and proofs of this theorem, but it was still named after him. But other than that, thank you.